The assignment is due today by 5 o'clock. So that's a little bit more time because normally they're due before class, but just because I got it loaded onto Blackboard a bit late on Monday, I wanted to give you some extra time. And then that way, if you have questions, you can check in with me. I've got office hours this afternoon, I think from 2 till 4. So the big thing on your mind, I'm sure, is the exam. We're going to have our first midterm exam on Monday, and we've talked about the conditions of the exam. I don't intend for it to be especially difficult, but you know, there again, I didn't think that the quiz was especially difficult, so shows what I know. I've got a little practice problem that I'm going to give you today related to settling, and the reason I offer it is just it'll have the practice problem and the solution on the back. This is just something that you can go through during the weekend to maybe get you more in the mindset of problem solving and kind of like the types of questions I may ask in a test. So this is just like more practice. Any questions on the announcements before we continue talking about sedimentation and specifically look at the in-class exercise? All right. So this is the one that we're going to start off with. This is a treatment plant that has a flow of 6,400 cubic meters per day. And we're going to neglect for now the fact that flow rates vary through the day. We're just going to assume maybe this treatment plant has a finished water storage tank at the downstream end of this treatment plant, which enables them to provide variable flows while still treating a constant flow rate through the day. So we're just going to assume that these people have the same flow rate continually. And what we know is that the settling basin dimensions are 2 by 9 by 18. And so you can see which dimensions I refer to. And the reason why it's important for you to know these dimensions in particular is remember that the surface area, that is the applicable surface area to calculate the loading rate, is that bottom surface area. So kind of interestingly, this isn't something that I talked about last time, the loading rate is independent of how tall the tank is. Like you could have a 1 meter tall tank or a 2 meter tall tank or a 3 meter tall tank, and this overflow rate, which is just an indicator of how heavily you're loading solids into the settling basin, stays the same. It's independent of how deep the water is. And the reason for that is that if you double the tank volume by increasing its height by a factor of 2, let's say the flow rate stays constant. So just think through this logically. If we went from 1 meter of height to 2, what does that do for the detention time? How long the particles spend inside of the settling basin? How long does the water stay in the tank if the tank volume doubles? Same flow rate. Remember, what we know is that flow rate is volume times time. No, sorry. Volume per time. That's more like it. Okay. So, for example, cubic meters per second, and then volume, cubic meters, time, seconds. Okay. So, how long the water spends in the tank. I've shown you this variable theta before. Theta just means like hydraulic residence time. How long the average water particle spends in the tank. So if we solve for that, it is the volume divided by Q. Okay, so if Q stays the same and we double the volume, what does that do to the residence time? Double it. I mean, this just makes sense. You got the same flow rate coming into the tank. If the tank is twice as big, then the water's going to spend twice as long in the tank before it goes out. But what I'm saying is that the settling performance isn't changed by the fact that the water is spending twice as long. And at first that's kind of counterintuitive because think about what these particles are doing during settling. is they're falling downward. So you'd think if you give the particles twice as long to settle, maybe that would improve your settling performance. What I'm telling you is it doesn't change the settling performance at all. That the settling performance only depends on the flow rate and the bottom surface area. It doesn't depend on the depth of the settling basin. And that's counterintuitive because the particles do have twice as long to fall. So why is it, you suppose, that by increasing the height of the tank, you're not improving the settling performance?
They have farther to go down.
They've got further to fall, and that's exactly it. If you've got a shallow tank, like the 1 meter, let's say we have this 1 meter depth tank, they've only got to fall 1 meter. But if you double it, now they're falling 2 meters, so twice as far in twice the amount of time. So it's just a linear relationship. So I wanted to point that out, that from a theoretical standpoint, the sedimentation only depends on the bottom surface area. Now, when that isn't the case, is if you make it twice as deep, then you may be improving how much of the settling zone is quiescent. And so, like, the practical effects can differ from that idealized description of, it doesn't matter if it's twice as deep, because if you can have it twice as deep, then you might be able to have more of the settling zone far away from, like, the bottom wiper. Remember that these settling tanks have a wiper at the bottom that can cause some disturbances. And so if the tank is really shallow, then more of the volume of the tank is under the influence of that wiping arm that could cause a little bit of disruption to the flocks as they're settling downward. But from a theoretical standpoint, the only thing that matters is the overflow rate. All right, so now back to this example. What we've got is 18 by 2 by 9. And so you need to know these dimensions because the A sub S is that bottom area. Okay, so we know the incoming concentration of solids, 250 parts per million. And the reason why we're going to use that is that here, this formula in the middle will tell us the percent removal of the particles. So the percent removal of the particles is related to a ratio of the settling velocity and the loading rate. Okay, so the steps here, I think in the handout that you've got, it says Part A, add the dimensions of the drawing to the clarifier. So I guess maybe I've already spoiled that opportunity for you because they're on the sketch there. Sketch the trajectory of the particle that starts at the top of the settling basin and then is just barely removed. Does anybody remember what we said the assumption is with the particle that's just barely removed? Like, by the time it gets to the end of the settling basin, where is it? The bottom right corner. So anything like the particle that's above that bumps into the wall, we assume that it flows out. That to be removed, it's that one that has to hit the bottom wall. So just sketch that trajectory. The critical particle is the one that starts at the top and just barely makes it to the bottom right by the end. So the interesting thing is we're assuming here that all of the particles have the same diameter. And that's never actually going to happen. This is just for purposes of illustration. But the interesting thing is that if you had a particle that's a smaller diameter, but it happens to enter the settling basin instead of at the top, but maybe in the middle, then it could be removed. So there is a distribution of where the particles start. Some of them start at the top, some of them start in the middle, some at the bottom. So there's a range of locations that the particles start their downward fall. And then in the real world, there's also a distribution of particle diameters, because you're going to have some very small pin flocks that didn't agglomerate very well and other really large ones that will settle quickly. But here, just for purposes of simplicity, we're assuming that all of these solids have a diameter that are spherical, number one, and that's how we use this Stokes equation, is we're assuming a spherical particle. and it's got a diameter of 1.2 times 10 to the fourth. Okay, so part C, I'm asking you to calculate the overflow rate. So that's with this formula, the loading rate Q divided by the bottom surface area. And then I'm going to pause while you go through that calculation to find V sub 0 and V sub S, the settling velocity. And I'll circulate around with the answer if you want to check the settling velocity versus the overflow rate. So I've got the calculations for the overflow rate and the settling velocity up on the screen. So I got a good question as I was walking around. Somebody asked me about, the units, and so you could convert the flow rate into cubic meters per second or cubic meters per hour. And since we're ultimately going to put both the overflow rate and the settling velocity into this formula that's a ratio, as long as Vs and V naught are the same units, then that's fine. And so here I've got it in terms of meters per day for both the settling velocity and the overflow rate. But you could have done meters per second and put it into this ratio and get the same thing. Okay, so part E is to calculate the percent removal. And then if you're removing a certain percent, part F is asking how much remains. So think about the difference between removal and remaining. And so use that percent removal to find out how many parts per million is going to be in the effluent still. Okay, so let's take a look at the percent removal here. The ratio of settling velocity and overflow rate tells us that we're going to be removing only 85.8% of the particles that have a diameter of 1.2 times 10 to the minus fourth meters. So if that's how much we're removing, then what we're removing is 214 parts per million of the original 250. So that means that 36 parts per million of this given particle diameter is going to remain. So this assumed that there's a perfectly even distribution across the inlet. This approach assumes an even distribution across the inlet. Now I add a thought question related to what if there were different particle diameters. And so I don't have it with me. What are the diameters that I say in this italicized part of the question?
1 times 10 to the negative fifth, 5 times 10 to the negative fifth, 1 times 10 to the negative fourth, and 5 times 10 to the negative fourth.
What was the last one?
5 times 10 to the negative fourth.
Okay. Okay, so what we had in this example was 1.2 times 10 to the minus fourth. Okay, so a particle that's bigger than that would be this 5 times 10 to the minus fourth. This is a larger particle. So this one's bigger, and so how is that going to be removed differently than the one we just did the calculations for? It's going to settle more quickly because it has a larger diameter, and so more of it would be removed. So you'd have more removal of that, but all the rest of this are smaller particles that would be removed less well. And so we'd see, on balance, a much worse performance of the clarifier if we had this distribution of diameters compared to the one that's mentioned in the problem statement. Because all these other fractions, was it 25% for each of the buckets? So 75% of the particles have a smaller diameter. They're going to settle more slowly. So overall, the performance of the clarifier would be worse for that distribution of particles. And so what you could do is, if you wanted to kind of think in terms of the real world, you do an analysis of what kind of particles are you trying to settle. Because there's going to be some sort of, like, I don't know if it would be a bell curve, but you'd have a distribution. They're not all going to be the same diameter. So, you know, it could be that maybe it is a bell curve, or it could be completely it doesn't necessarily have to be reflected across some central axis. It could be a variation where some of the particles are, in terms of increasing diameter, a small fraction of them are really big, and so you could say, I'm going to choose a certain diameter to represent that population and see how well it settles in a certain design. And then you'd pick a certain diameter to represent this next population, and you'd find out what the settling performance is, what's the percent removal. And so you could do that, breaking it up into segments, represent that segment by some central diameter, and then predict the performance, the percent removal for each of those, and then have an overall weighted average of the percent removal based on the distribution. Any questions about the example before we move on? So all of this was type 1 settling. Type 1 settling, just to remind you, is where we assume the particles achieve some terminal velocity. There's other types of settling, though. In type 1, it assumed that the particle settles down, and as it does so, it never encounters other particles. It's not getting bigger by bumping into other things. Type 2 assumes that the settling velocity is increasing as the particle goes down, because particles are still bumping together and flock is growing inside of the clarifier. So type 1 is a constant settling velocity. Type 2 is an accelerating settling velocity. And type 3, the settling velocity is getting slower because the particles are interfering with each other. They can't settle down as fast as they'd like because there's other particles in the way. So it's kind of interesting. Constant, increasing, and decreasing settling velocities are how we differentiate these different types. And so in type 2 settling, the particles are getting faster because they are bumping into each other, and the way that you would estimate the effect of this type 2 performance, where the particles are actually growing as they're in the settling basin, is you just have to do a bench scale experiment where you take a sample of the liquid that's being settled, and you would, over time, measure how much of the removal has occurred at a certain depth. And so, like where it says here, 15, 19, and 41, that's the percent removal, and you'd have some sort of a tap in this cylinder that you could suck a little bit of water out. So, you know, if this is our starting depth at time equals 0, this is saying go down into the fluid 0.5 meters, and you draw off a certain portion of the liquid. So you could do that by putting a pipette in and taking a sample out, or it could be that there's just a hole on the side that you draw a little bit of fluid out, and you'd see how many of the particles have been removed. And so in this hypothetical example, you've got 41% removal at a depth of 0.5 meters after 5 minutes. And you go a little bit deeper into the fluid and you have less removal, 19% removal, 15% removal. So then you keep doing that for a 2-hour period. Every so often you are measuring the percent removal at a different depth, and then you could draw these contour lines that kind of represent how long you'd have to wait to achieve a certain percent removal at a given depth. And so, for example, this 60% curve, you're just going in between the point measurements and interpolating a little bit to identify if you want 60% removal at a given depth, how long you'd have to wait. So this can be used to give you a sense for how deep the clarifier should be if you're experiencing type 2 settling, and also the hydraulic residence time. And a typical rule of thumb is if you do this lab test and you're kind of designing your process around a worst case scenario, so you don't assume that the coagulation flocculation process is perfect. You assume maybe you have your highest turbidity input water and kind of compromised performance with coagulation flocculation. So it's kind of just like a marginal level of settling that you think that you can achieve most of the time is how you design your settling basin for. And then you'd find out how big the settling basin needs to be based on this testing, and then you'd double it. They put in really generous safety factors because the consequence of not having effective removal of these particles is that it can affect human health. And so there's just enough variability in the conditions that affect settling that they generally would provide a pretty healthy factor of safety. So that's type 2 settling. Now type 3 is where the sludge particles down at the bottom of the tank are interfering with the ability of the flocks above it to settle down as quickly as the flock would if there was nothing below it. So sometimes we can see like a blanket of sludge forming, and this is where you'd have very high solids content. And once again, you'd have to do a laboratory experiment. I'll show you a video of what a settling velocity lab experiment might look like. Let's pull that up. Okay. So they take a sample of the fluid the liquid that needs to have settling done. And he's demonstrating right now that you need to be really careful when you've taken a sample not to agitate it too much, because if you mix it quickly, then that could break apart the flock. So there's all sorts of problems in taking a test like this. You want to make sure that this is a representative sample. So you'd have to take it from, if you already have an existing settling basin, you'd have to take it from a representative conditions with your inflow water quality, with the dose of coagulant that you're going to use, with typical conditions in the flocculator. So you want the sample to be a good representation of what you hope to treat. And then they put it in a wide mouth jar. And it can't be too narrow for this. Now, by the way, I'd quibble with the way he's pouring it in there. I mean, just the amount of energy that's going into pouring the water in could break apart the flock. So you know how you're supposed to pour a beer like in the side of the can so it doesn't get too much foam? I think that's what he should have done here too, is pour the liquid gently in the side of it, let it transfer from one to the other without too much agitation. So I've got to quibble with the way that it's being poured in. And you basically just wait. And you'll notice that this is graduated where it's got the volume indicated. And so he's mixing it gently just to make sure that there's an even distribution in the flock. And making the point that you don't want to stir it too hard, but there's going to be a graph of over time, where do you see clear water? Okay, so this particular sludge, you can see there's a really distinctive layer between where the majority of the particles are and the clear supernatant above it. The supernatant is the liquid that's above the layer of sludge. And over time, you're just graphing where that most distinctive layer is. And you can use this data to calculate something called the sludge volume index, which we'll talk about in a minute. Now, this type 3 settling is most common for wastewater treatment. But with this chapter in the book, it kind of is talking about principles that apply both to drinking water and wastewater processes. So for the most part, we're talking about drinking water treatment right now. But I wanted to point out that this is not water that had been flocculated for drinking water purposes. That this is probably a wastewater sludge that they're wanting to get the settling performance for. All right, so it's just a graph of how much volume is occupied by the sludge at a certain period of time. The sludge volume index, SVI, is the settled volume of sludge at a certain time divided by the concentration of mixed liquor suspended solids. And mixed liquor suspended solids is something we'll talk a lot more about when we're in the activated sludge portion of the course. But it's basically just the concentration of solids at the beginning of the treatment process. So overall, how many grams of solids are there per liter of sample? And then this milliliters per liter is you have a liter of water that you were settling to begin with, and then after a certain time, whether it be 15 minutes, 20 minutes, the sludge volume index is relative to whatever time frame you want to designate. What's the volume of the sludge occupying of the overall 1 liter that you were starting with? And if you've got an SVI of less than 80, that means that the settling is really rapid. You know, it's sinking to the bottom really quickly. But the problem with that is if it's settling really quickly, then that must mean that the flock particles overall are pretty big, and it's not doing any kind of filtration of the particles beneath it as the sludge blanket settles. An SVI of between 100 to 200 is maybe better from the standpoint of effluent water quality because the sludge blanket, as it's falling downward, acts as a filter. So let me go back to the video. Okay, so under here is a lot of water that's having to be squeezed upward through this sludge blanket as it's settling downward. And so some of the small particles that maybe wouldn't have been trapped as easily, they get trapped because there's this mesh of solids across the top that's kind of like a sponge or a screen. And so this kind of middle range SVI is advantageous because it helps to encourage the screening effect. So from a water quality standpoint, SVI of 100 to 200 is ideal, but any higher than 250 and just the settling performance is so slow that it's problematic. And there's the possibility that you may have slow settling because there's something called filamentous bulking. It could be that there's algae growing in the settling basin that links together the particles that are supposed to be flocculating, and it's considered a bad thing if you have filamentous bulking. It's just that there's you can think of it as like these strands running through the sludge that kind of suspends it and prevents it from settling as much as it otherwise would. There's just an internal structure there that's keeping it from settling downward as rapidly as it ought to. So we'll talk more about zone 3 settling again when we get into the wastewater portion of the course, but that's the overview of the 3 different types of settling. Now we have to get the water out of the settling basin after the settling has occurred, and so the way to do that without disturbing the flock as it settles down is to have a large cross-sectional area for the exit. So you can't just have a pipe at the end of the settling basin. If you just had a single pipe, then the water would have to accelerate too quickly through there. So think about velocity is flow rate divided by area. And what we want to do is we want the water exiting the tank to have a low velocity. Because if it has a big velocity, it's going to get into the settling zone and disturb the particles that are settling down. And so we want the water that exits the tank to exit the tank really slowly. So in order to do that, to have that slow exiting performance, we have to have a big area, a large cross-sectional area for the water to exit. And so having a long array of weirs, and this array of weirs is called a launder. To have all these, here it's V-shaped weirs, and the water is going into this trough, because when you have a really long array of weirs like this, then the water is exiting the tank at a slow velocity, because you have such a big cross-sectional area. Rather than just a single pipe, you've got all the area of the weirs. So that's a way to distribute the effluent so that it doesn't scour out the settling zone. Typical overflow rates for a weir in drinking water treatment are determined by the nature of the flock that you're trying to settle. And so the heavier the flock is and the easier that it's going to settle to begin with, then you can kind of crank up the weir loading rate a little bit more. And so the units for this weir loading rate are how many cubic meters per day you are loading relative to each meter of weir length. And so here in the denominator of the units, the meter that they're talking about is the length of the weir. It's not necessarily the physical length traced by the V notch, but it's just how many linear meters of V-shaped weir you'd have. Now, look at this configuration. Why do you suppose they would have, like, why not just have a straight line and have the water flowing over that straight line? Why this kind of sawtooth configuration? What do you suppose is the point of that? It's more length, right. If it was a straight line, it would be less length down here in the denominator. But when they have it sawtoothed like this, you'd find the overall length, which I'm tracing right now with the cursor. So it's a way to pack in more shoreline for a certain linear distance, is by having that sawtooth pattern. And so here's another way of increasing the length of the launder when you have, like a fixed linear width at the end of the settling basin, and if that's not enough, then you could increase the distribution of where the water's going out by just kind of protruding into the flow a bit and having the launder on either side, and the water can exit at a lower velocity with the more area that you're spreading it out over. So here, we've got the water coming into a central trough from both sides. So just to illustrate this calculation of weir loading rate, I put together this example where we have the same clarifier as the last example and the same flow rate. Let's say that we are putting a weir at the end of the clarifier up at the top. Remember that that's 9 meters wide. So I wanted to illustrate the calculations for the weir loading rate if we just have a single side, meaning, like, what if we just had the water coming to the end of the clarifier and we don't have the water entering a central trough from both sides, but if we just have it coming in from one side. So the way that we would calculate that weir loading rate is you've got the flow rate per day, 6,400 cubic meters per day, and it's exiting the clarifier over a length of 9 meters. So that loading rate would say that we've got 711 cubic meters per day per meter. And that's not going to be acceptable for any of these flock types. Nothing would allow us to get away with having 711 cubic meters per day per meter. So instead of having a single-sided launder, what about the weir loading rate if we had it double-sided? So here again in the calculation illustration, we just double the overflow length. That still puts us in the 356 cubic meters per day. And so let's say that we were doing a heavier alum flock, and we wanted to be kind of in the middle range here of 200 cubic meters per day per meter of launder. So if we wanted to design how much length do we need to achieve to get that loading rate, then this time we're solving for the unknown distance, and we know we want a loading rate of 200 cubic meters per day per meter. And this is our flow rate coming into the clarifier of 6,400 cubic meters per day. So we're just solving for the unknown distance. If we had a length of 32 meters, then that would give us the loading rate that we need of 200 cubic meters per day per meter. So to achieve 32 meters of length, but if it's only 9 meters wide, we'd probably have to do something like this. We'd have to have it protruding into the clarifier a bit, and then we could add up the cumulative length. So, 1 meter, half a meter here, another meter, here's another meter, then half a meter. You'd add up the overall perimeter, and that's what you're going to use for the overflow. Okay, let me hand out this additional problem-solving practice for settling. This is a test question that I gave 7 years ago when I taught this class at another university. So I guess I can't reuse this question now that I'm giving it to you as an example. All right, I could, right? I'd give some incentive to the people who looked at it. You wouldn't complain? I feel like I was shortchanging you if I did that.
Well, just give us 100% on one question.
Okay, then were you?
Yeah.
Okay, so the problem's on the front, the solution's on the back. Just another chance to get some practice. Any questions before we go our separate ways for today? So then we will have our celebration of learning on Monday then. All right, have a nice weekend.